What time tells us? An explorative study of time awareness learned from static images. Why is time awareness important? Clock time is an established conceptual norm that organizes human life. It shapes how we perceive and navigate the world. Visually, humans rely on environmental cues like light and shadows to intuitively understand the time of day, from which mature clock systems came into being. This inspired us to ask, can neural network develop similar time perception capabilities? If so, what implications such time awareness help us in broader recognition of visual scenes? To answer these questions, we start with a pretext task estimating clock time from solely images and analyze the implications of the estimation model on downstream tasks. First, we introduce TOC, a benchmark dataset on pretext tasks featuring diverse natural images with verified timestamps, addressing limitations in prior datasets. Our dataset, TOC, includes over 130,000 natural social media images across training and test sets, each with manually verified timestamps. Second, we propose a novel learning paradigm called Time Image Contrastive Learning, TICL, which achieved SOTA performance for pretext timestamp estimation task. In addition to the contributions on pretext tasks, our primary focus aims to demonstrate the implications of time awareness in several zero-shot vision downstream tasks, including time-based image retrieval, video scene classification, and time-aware image editing, which revealed clues of the source and implication of time awareness from visual inputs. At the heart of our learning framework is TICL, which bridges the gap between clock timestamps and image features. The key idea is to align time and image representations with rich semantics from a foundation model in a shared space using contrastive learning for the pretext time estimation task. This paradigm not only surpasses prior methods in time-of-day estimation but also opens new avenues for downstream tasks. For a deep dive into our implementation, refer to Appendix B, which includes technical details and comparisons. Our experiments validate TICL's effectiveness on the pretext clock time estimation task. On TOC, TICL achieves a significant improvement in different metrics, outperforming prior baselines with higher accuracy and smaller mean absolute errors. Additionally, it generalizes well to unseen datasets like AMOS, which we use for zero-shot evaluation. There are additional error analysis and results, detailed in Appendix B, providing more details about the capabilities and performances of the learned model on the pretext task. To better understand and justify TICL's design, we conducted ablation studies. We found that the clip image encoder with rich semantic awareness provides the best performances over all the pre-trained backbone models. In addition, both the time encoder and image time adapter contribute jointly to the best performance when combined. We also find that for our proposed paradigm, using rough time class encoding outperforms previous vector encoding methods that are supposed to be more precise in terms of representing clock time. Appendix D provides additional explorations and ablations to the inherent trade-off in terms of time encoding precisions using either lossless scalar encoding and fine-grained class encoding. One downstream task we explored is time-based image retrieval, where the objective is to retrieve images captured at times similar to a query image. TICL achieves the highest performance across recall at K metrics, as shown in the chart. Additionally, the time error distribution demonstrates TICL retrieves a higher proportion of images with minimal time differences compared to other methods. For more details, see Appendix D, which includes expanded visualizations. Another downstream task is video scene classification, where TICL leverages time awareness to improve classification accuracy. For example, on the Hollywood 2 scene dataset, TICL significantly outperforms previous baselines and other pre-trained image features. This improvement indicates that, despite the scenes are supposed to be invariant with regards to time of day, there are indirect relations learned between visual scenes and clock time, as we have shown in the TSNE visualizations and the probability distribution of text queries over different time spans. For further implementation details, including analysis, see Appendix E. Lastly, we applied TICL to time-aware image editing, enabling modifications that accurately reflect specific times of day. Compared to purely text-guided methods, an additional TICL loss term produces more realistic and time-consistent results in a latent optimization image editing baseline experiments. For instance, in the example shown, TICL captures natural lighting transitions for morning and evening scenes across different subjects. Detailed implementation including quantitative evaluations and additional results of editing using diffusion models are available in Appendix F. In conclusion, this work introduces the TOC dataset, a benchmark for natural and reliable time-of-day estimation. We also propose TICL, which sets a new standard for this task. Beyond pretext clock time estimation task, TICL demonstrates its versatility across downstream tasks, enhancing image retrieval, video scene classification, and image editing. These results underline the potential of time-aware embeddings for advancing visual scene understanding.